Good morning, good afternoon, good evening, whatever time you're watching this. Hello, I'm Montesclaros of Group 5, along with my colleagues Stephen Alorro and Carlo Eslit. We're here today to discuss basic propeller principles. First, our objectives are being familiar with the basic propeller principles, being knowledgeable about propeller theory, and understanding of propeller pitch. First off, what is a propeller? The propeller's function is to supply a means of propulsion so that the aircraft can fly through the air. The propeller is made up of one or more blades joined by a hub in the center that attaches the blades to the engine shaft. Because the propeller blades resemble an airplane's wing in design, they may generate lift, or also known as thrust, by rotating when an engine is running. This lift allows the aircraft to travel forward. Next up is, how does the propeller work? The third law of the three laws of motion that was formulated by Sir Isaac Newton over 200 years ago is the basis for the principles underlying propeller operation. The third law of motion, which states that there is an equal and opposite reaction to every action. An aircraft's propeller is used to convert an engine's rotational output into forward thrust, which is the action, and the airplane is then forced forward by the consequent pressure difference as a result of the air movement, which is the reaction. The amount of thrust or forward propulsion produced increases with the amount of air drawn behind the propeller. Next up is parts of the propeller. We have the blade tip, the cord, the trailing edge, the leading edge, the hub, and the blade tip. Here are the definition of terms. The blade is one arm of a propeller from the tip to the hub. Propellers usually have two or more blades. These are blades right here. Next is the leading edge, the forward or cutting edge of the blade that leads in the direction the propeller is turning. So here, right here, the angle that is leading towards the front of the propellers, that is our leading edge. And here, the trailing edge, also known as the rear edge or the back portion of the propeller, is just simply the back portion of our leading edge right here, which is the behind of the angles. And now the shank, the thick portion of the blade that is near the hub. Here is the shank, that is the intersection of the propeller blades and the hub right here. And now the hub itself, the central proportion of the propeller that is fitted to the propeller shaft, purpose being to secure the blades by their roots. Here is our hub right here, our center. And the tip, it is the outermost portion of the blade, the portion of the blade furthermost of the hub. And the name itself is very self-explanatory. Here's our blade tip, the very edge of our blades. Next is the blade face, the surface of the blade as seen by standing directly behind the propeller. So the blade face is the point of view of our pilots, where they can see from back behind. That is our propeller blade face. And a blade back, the surface of the blade as seen by standing in front of the propeller itself. Depending on the particular aircraft's efficiency requirements, propellers might consist of one blade, six blades, or even more. The primary factors influencing the number of propeller blades are engine power and aircraft performance standards. To effectively use the extra power produced by the engine, more blades are required as engine power increases. The amount of thrust produced is dependent on the propeller size, shape, and angle of the blade alignment. Next is Propeller Theory by Carlo Eslit.
Hello everyone, my name is Luis Carlos Eslit, so I'll be discussing the propeller theory. In the propeller theory, rotational motion at the crankshaft is produced by an internal combustion engine by means of piston reciprocating motion. Afterwards, the propeller transforms this rotational motion into a forward thrust force, propelling the airplane forward and balancing the drag created passing through the atmosphere. Because of the manner of the propeller blades are made, they are influenced by many of the same aerodynamic factors that affects the wings, like lift and drag. The added force of rotational speed and forward-acting momentum included in the propeller make a difference. So this theory explains how a propeller creates a forward motion or a thrusting force by by the difference in pressure or through um, the airfoils of an airplane. So next is the engine and propeller combination. A propeller needs to be built to cooperate with an aircraft's engine, not to function independently. An aircraft that does not satisfy the performance standards specified by the aircraft designer will at best be the consequence of poorly selected propeller engine combination. In the worst case scenario, this would result in the fundamentally hazardous aircraft that, what, that might have trouble taking off and be vulnerable to an engine and propeller failure while in flight. So next is the propeller forces. Through the rotation of its blades, a propeller transfers momentum from the air to the propeller, producing thrust. You can think of thrust produced as the response to the acceleration of an air column whose diameter is equal to the propeller. Momentum is the product of mass and velocity. Through the rotation of the blade, the propeller cuts through the air, creating a forward motion or a thrusting force. So next is the angle of attack. All that a propeller blade is a wing with a twisting section of airfoil that revolves around the axis perpendicular to the plane's direction of motion. Similar to a traditional wing, a propeller blade generates lift and drag forces corresponding to the square of velocity at which the blade passes over the surface. The resultant velocity of the propeller is dependent on both the forward flying speed and the rotational speed of the blade, in contrast to the aerodynamic forces of a wing, which are determined by an aircraft's forward speed. The angle of attack at a given blade angle decreases as airspeed increases because the airspeed component of the relative airflow increases. On the other hand, the angle of attack increases at the lower airspeeds. So I'll be handing over the next topic to my colleague, Stephen Alorro.
Hello everyone, I'm Stefan. I will be explaining the forces acting on a propeller. According to Newton's third law, there must always be an equal and opposite reaction to every action. The propeller gives the air around it momentum, which generates a thrust and torque force. The air's motion on the propeller reacts to this by imparting a series of forces. Every blade on the propeller receives force from the engine's torque. A propeller needs to be robust enough to withstand every force applied to it during the whole design envelope. One of these is the centrifugal force. The rotation of blades creates a centrifugal force that seems to desire to pull the blades apart. This pulls the blade in tension and is the main force of operating on an propeller. Next is thrust bending force. It tends to bend the propeller blade forward at the tip due to the thin blade portions being bent forward by the lift at the blade tip. Next is the torque bending force. It possesses a tendency to bend the propeller blade back in the opposing direction of rotation. The air resistance prevents the blade from rotating. Aerodynamic twisting force aims to use aerodynamic action to twist a blade to a higher angle. The centrifugal twisting force tends to counter the aerodynamic twisting moment and reduce the blade angle. Propeller pitch. A propeller's blades are angled much like a screw rather than being straight. Pitch is essentially a measurement of the propeller's forward motion per revolution. The propeller's pitch is utilized to regulate the airflow speed exiting the rear. As you travel from one end of the propeller blade to another, the pitch of the blade changes. It is shallowest at the outer tip and steepest or shortest at the center hub. Pitch equals 2.36 diameter height divided by width is the formula used to compute the pitch. That's all.